Hi there. Today we are going to talk about mesh analysis. My name is Vivek Subramanian.
And I'm Michelle Maharbiz. Let's get started. Okay, so today we're going to teach you a dual to nodal analysis called mesh analysis. And you're going to see as I talk through that there are dualities or similarities in a sense to nodal. Okay, so let's start with the circuit. We've got 3 resistors and we've got an independent voltage source V0. And we've got this extraordinary node here. Now, when we were first talking about basic circuit concepts, we mentioned the notion of current loops, and I'm going to use that terminology here, except I'm going to call them meshes. Okay, and so what you have to just observe by looking at the circuit is that there are these conceptual current loops that can flow in a closed path. Okay, so let's just take a moment and look at that. There is this conceptual current I1 which flows around in a circle starting from, say, the bottom left corner and going around. The key here is that it follows a closed KVL path. Like when we were doing KVL, remember we were doing KVL around loops, so we started here and worked our way around and came back and said that the total potential drop was 0 once we got back to where we started. If you recall, we did that. So this is what this mesh is doing. Okay, and it's a concept. For the moment, I don't want you to worry about what the actual current actually means. You'll see why I'm saying that once we start doing the math. But it's basically this conceptual current that's running around in a circle. There's another one here.
So if I understand correctly, what you're saying is anytime we see a loop, just draw a current path and we'll then do something with it.
Yeah, exactly. And when you could even draw one just like when we were talking about KCL. You could be a mesh that goes all around this outer thing out here. But for the moment, we're gonna be looking at this I1 and I2 mesh.
So we'll pick the minimum size closed paths that we see and just draw circles with them.
You're jumping ahead, but yep, that's what we're gonna do. So let's, for convenience, also follow our clockwise rule that we've already been sort of adopting. We're gonna adopt it for our mesh analysis too. Okay, so now I've labeled them. So the key for step 1 is I'm labeling these mesh currents in every one of these little loops, these internal loops, as Vivek said. Remember, when we were doing nodal, we were labeling our nodes, and they were voltages. Here we're labeling these meshes, these loops, and their currents. Okay? Now the second step is, once we label them and the direction, we're going to just write KVL around each one of them. Okay? So we're pretty good at KVL now. So looking at mesh 1, I'm going to start down here at the bottom left on the negative terminal of the independent source, and I write minus V0 plus I1, don't worry about this IA here for the moment, I1, this is my mesh current, times R1. Notice that and this is where students get tripped up, notice the current is going from left to right, it's going clockwise, so for the purposes of this resistor, it's going from left to right, so I1 times R1. Now when I get to this R3, here's a little bit tricky. What's the current going through this resistor R3, okay, in terms of mesh currents? That's the key. Well, I1 is running down, because it's going clockwise, it's running down R3. But notice this I2 is running up R3. See, I2 is running, they're both running clockwise, so see this is going up. So the total current as expressed as a function of only the mesh currents, these hypothetical mesh currents, is I1 minus I2, right? Because they run in opposite directions, times R3 equals 0. And of course, at that point, we're done. We've gotten back to where we started, equals 0. Sorry. So minus V0 plus I1 R1 plus I1 minus I2 times R3 equals 0. That's the first KVL around this mesh. We can do this again for this mesh I2 going around this mesh here.
Let's take a minute
Sure.
for you to think about it and come up with the KVL on your own. Look at the KVL that you see there and see if you can explain why we've got it, and then we'll review.
Okay, so let's go through it. Again, we're going to start bottom left, so we're going up through R3. What's the current, the total current through there? It's I2, which is going up, minus I1 times R3, right? That's the voltage across R3, plus I2, that's the only current that's running here, times R2, and then we're back to the beginning where we started on our loop, equals 0. So we've got two equations, two unknowns, because I1 and I2 are the two unknowns, and everything else is either a known independent source or the resistances. And now we can just solve them. So you can solve these two equations trivially. You can solve them using matrix math. However, it's very common, just as we did with nodal, where we were lumping everything into V1, V2, and V3. Notice here what I've done is I've gone from this equation up on the left to I1 times the resistances, and then I2 times resistances equals, and then the thing on the right is due to the source terms. And intuitively, you can see it makes some sense. This equation, which deals with a mesh that touches on an independent source, has something on the right-hand side. That's the forcing part of this equation. Whereas this one, which has no source on it, has 0. Okay? But in both cases, there's something in front of multiplied by I1 and something multiplied by I2. And you can solve this system. Now, I have to tell you, before we do a few examples, I find that mesh current analysis can confuse students, because when they start labeling these loops, that part's easy. Step 1 tends to be fairly easy. But then when they start to try to write the KVL, they get these I1s and I2s, what you subtract from what, confusing. And in the end, you get math errors. But we're going to do our best to give you a bunch of examples so that you can get pretty good at it. And it's a pretty handy tool as a dual to nodal.
And one trick to keep in mind with respect to that is when you're just trying to figure out which currents to add and which currents to subtract, the currents within the loop that you are actively dealing with at that time will usually be positive. And
that's a good point.
the
Yeah.
adjacent loops will usually result in negative currents. And when we do this example, you'll see that here.
That's a good point.
Okay? So here I'm giving you a circuit, and I want you to find Ix. Okay? Now this circuit's a little more, we made it a little more difficult because we've added in a dependent current source. Specifically, this is a voltage-controlled current source. So we're going to work on this one together. And we've got 3 loops, so I will define 3 mesh currents, so I1, I2, and I3. So let's look at mesh 1. So I'm going to start at the bottom left of mesh 1. I've got minus 10 volts coming through the source. And then I've got the voltage across the 1 ohm resistor. So that's going to be I1 minus I3 times 1. And so again, you see the loop I was actively dealing with is positive. The adjacent loop is negative. So I1 minus I3 times 1 plus 2 ohms times I1 minus I2. So we've got everything put together. So it's minus 10 plus 1 times I1 minus I3 plus 2 times I1 minus I2 is equal to 0. And that's the KVL equation for mesh 1. Now let's do mesh 2. Mesh 2 means I2 is the current we're actively dealing with, and I1 and I3 will be the adjacent ones. So we'll have 2 times I2 minus I1 plus 1 times I2 minus I3 plus 3 times I2 is equal to 0. And so we've now completed the KVL on mesh 2. Mesh 3 is a little interesting. Mesh 3 is interesting because it's actually much easier to deal with. And the reason it's easier to deal with is, remember, ultimately we're trying to find the currents, I1, I2, and I3. Well, I know what I3 is. And the reason I know what I3 is because I have a current source there. The current source tells me that I3 is equal to Ix. And I know what Ix is. I've been told that Ix is equal to 4 times V1. So for mesh 3, I don't actually have to write the full KVL.
If it was an independent source, that would be the end of it, because then you'd get I3 equals some number, say 5 amps. But in this case, now it's equal to V1, but V1 isn't a current, and we're only solving for current. So what are we going to do?
That's right. So we don't know what V1 is on its own, but we do actually know what V1 is, because V1 is the voltage across the 2 ohm resistor, and you know what that is. That's the current through the 2 ohm resistor times 2 ohms, and the current is going to be?
I1 minus I2, that's the current,
right?
And then times the 2 ohms, that gives me V1.
That's right. And you picked I1 minus I2 as opposed to I2 minus I1 because the positive is on the top.
That's exactly right.
Okay? So we can now take these equations from mesh 1, mesh 2, and mesh 3, and we can collect them the way we did in the previous slide, where we collected all the current terms on one side and the source terms on the other. And then we can deal with that one dependent source that we had earlier. In other words, we write V1 is equal to 2 times I1 minus I2. And now we can we can plug these in to solve the equations. We've now got equations in terms of I1 and I2 only. I3 went away because we had defined it in terms of the voltage. And so when we solve, we can now find I1 and I2, and it turns out I1 is minus 14 amps, I2 is minus 10 amps. If we know that, we can then find Ix, because we now know I1 and I2, so we know V1. And if we know V1, we know Ix.
And the other thing I noticed is from these conceptual mesh currents, I1, I2, I3, we could also answer things like, what's the current through the 1 ohm resistor between mesh 1 and mesh 3, say this one, right? Because basically the current through this is I1 minus I3, and I can literally just do that subtraction. Minus 14 minus 10, right?
That's
Gives me
right.
Minus 4.
That's right. The other nice thing about this is it also directly tells you the current through sources. So you know that the 10-volt source is delivering 14 or minus 14 amps in terms of the definition of the arrow.
Right. Okay, so it seems to me that to take a quick aside, in Nodal we were labeling node voltages and doing KCL around each node and solving for node voltages. We wanted V1, V2, V3. In this, we're labeling meshes and doing KVL and solving for the mesh currents.
That's correct. By the way, since we're on this topic, I think there's a good aside we can have over here. Let's look at that voltage source, the 10-volt voltage source. And the current coming out of its positive terminal is minus 14 amps.
So that it's like having positive 14 amps go down into the positive terminal.
So this is an interesting circuit. It's actually charging the battery.
Oh, so your point is by the passive sign convention.
Right.
We would immediately know that this is actually not supplying power, it's consuming power.
Right. So if this is a battery, this is effectively charging the battery. This is a circuit where this dependent source is actually delivering more power than the circuit actually dictates on its own, such that it is actually charging the battery.
That's an interesting observation. I love the passive sign convention.
Yeah, the passive sign convention is useful because it allows you to look at these things. By the way, don't build this circuit with a regular battery at home because you will cause, at some point, the battery will explode.
Good to know. Okay, so now there's an analog to supernodes in nodal analysis. We saw supernodes. There's an analog to this called supermeshes in mesh analysis. And what were supernodes in nodal analysis? It was cases where we had a voltage source between two nodes such that we couldn't write the current equation we needed, the KCL. Just by duality, what a supermesh is a current source. It may have a resistor in series, and I'll come back and make a point about that, or it may not, but there's a current source that is shared by two meshes. You see here I2 and I3 have a current source running between them. And the problem is that once you introduce a current source there, what do we know about the current source?
Well, we know the current, but we don't know the voltage, which causes a problem for KVLs.
That's right. We can't write a KVL around I2 or I3 simply. We just can't write it. And so we're going to have to come up with a way of dealing with it, just like we did with nodes. Now, in the same way as an independent or, say, a dependent, a voltage source, in the same way a voltage source could sit with a resistor in parallel and be considered a supernode. If you go back to the previous lecture, we discussed that. You can have a resistor in series with this current source. And that's because it doesn't matter what this resistance value is. I0, this current, will always run through that resistor. It makes no difference. And so it's just going to work itself out. Okay?
That's fine. And remember, the reason for that is the super mesh auxiliary equation, as you'll see, is going to be a KCL.
Oh, you're jumping ahead, Vivek. All right, so the bottom line is we have a voltage across a current source that we don't know. We just don't know what the voltage across this current source is. Okay? So what we're going to do is we're going to build a super mesh. That is a mesh loop that includes both of the ones that share the current source. And we're going to write KVL around that big one. And that's going to be fine because it doesn't include this source at all, so that'll be easy. And then we're going to write a auxiliary equation, as Vivek just hinted at, which is a KCL equation for that branch that's shared between the two. And you can see immediately the analogy to the supernode, where we wrote a KCL for the whole node, and then wrote the KVL auxiliary equation. This is sort of the inverse of that. And so here's our super mesh, and we would write KVL around the super mesh. For this resistor, so let's say we started at the bottom left, we'd write the R5, R2, R3, and R6. So those would be the 4 terms to our KVL, and then we would come back and do a KCL for the shared branch that includes the current source.
Now remember, the reason it works this way is any current that is being pulled through the left-hand side of the super mesh will be then delivered on the right-hand side.
Oh, I see.
So any reduction of voltage on one side is going to have an increase in voltage on the other side, or vice versa. So the KVLs are going to work out the same no matter what.
There you go. That makes perfect sense. So let's work an example. In this example, we've got an independent voltage source here, and we've got an independent current source here. And you can imagine this independent source is going to give us some trouble. So we start by naively labeling all our mesh currents. That's the correct thing to do. So we've got them all clockwise. I1, we call this one I2. This is inside this little triangle. We've got I3 running around here between this resistor and this source. And we've got I4 running around the loop that includes the 3 amp source, the 2 ohm resistor, and the 4 ohm resistor. So far so good, except we're already detecting something fishy because we're going to have a problem with KVLs and this 3 amp source. Oh no, now we know that it's a super mesh. And so what we're actually going to do is we're going to write, when we get to this point, we're going to actually write a super mesh equation, KVL equation, around these 2 meshes, I3 and I4, around the periphery. So we're going to have 3 basic equations and then our auxiliary. In other words, we're going to do the I1 mesh equation as normal. We're going to do the I2 mesh equation as normal. But when we get to I3 and I4, we're going to have one combined equation. That's the super mesh equation. And then we're going to come back, and the fourth thing we're going to do is write a KCL for this 3 amp. Now, what I'm going to do is I'm going to show you the equations for the meshes in a way where we've already factored out the currents. And that's to have you do a little bit of exercise. I'm going to walk you through it, but it's really to have you exercise, do it on your own, and make sure that you can arrive at these correct expressions. So if I was writing it from scratch when I do KVL, my KVL is going to be -6, because I start at the bottom left and there's a minus, plus I1 times 10, plus 2 times I1 minus I2, plus 4 times I1 minus I3. That would be, and then I'd be back on the bottom left. That would be for I1. Now, I've done it quickly, with speech, so that you can go ahead and try it on your own and make sure then when you factor out, you get this. I'm not going to do mesh 2. I'm going to leave that for you. It's fairly straightforward, so that you can try your hand at it and see if it matches.
You'll notice if you look at these that, as we discussed earlier, for the loop that you're actively dealing with, all the coefficients are positive. And for all the currents associated with the adjacent loops, the coefficients are negative.
That's right. So it's exactly what Vivek's been pointing out for the whole lecture, that, say, take I1 for mesh 1, these are all positives, no negative number here, and for I2, these are positive. Now we're at mesh 3 and 4, which is the sort of tricky one, our super mesh loop, but it's really not that tricky. So I'm going to give you the complete expression, but we can just start at the bottom left and work our way up, right? So going up through here, we have 4 times I3, minus I1, and then here continuing around, we've got 2 times I4 minus I2, and then getting to the 4 ohm resistor, we've got 4 times I4, and we're back to the beginning. So don't just because you're a super mesh, you shouldn't feel like both I4 and I3 should be in every one of the KVL expressions. It really is just as though you were doing a normal mesh. You're just going around the outside of both of them using whatever terms you need. Now, the problem is, of course, that now we've got 3 equations, but we've got 4 unknowns, I1, I2, I3, and 4. But this is where the auxiliary equation comes to the rescue. And in this case, it's pretty easy. And the reason is that we know, just by inspection, by looking at that I3 minus I4 is minus 3 amps, or conversely, I4 minus I3 equals 3. And you can see I4 is running clockwise, so it would run in the same direction as the 3 amp source. So I can say that I4 minus whatever I3 subtracts from it equals 3 amps. Okay, so that's the super mesh auxiliary equation. And we've got enough there to solve. At that point, we solve however you want, matrix or elimination or Wolfram alpha, and you get yourself some numbers.
So can you tell me anything interesting you see about the voltage source in this particular problem?
Well, let's go look at it. So you're talking about the 6-volt source.
Yep.
And I1. Oh, look at this. There's no current running through it. So I guess all the power, well, let's hold on. So it would be interesting to go back and look at the voltage across this. And I guess what you're suggesting is all the power for this circuit is coming out of this source here, the 3-amp source.
That's right. In fact, the way this circuit is set up is it's set up such that ultimately the voltage that is seen at the terminals of the 6-volt source is exactly 6 volts, such that no current flows through that 10-ohm resistor. In other words, if you look at this point up there, that point is going to be biased at 6 volts.
Well, reference to this point.
Reference to the bottom point.
And you know, that points out another interesting thing. We haven't put ground on any of these circuits.
That's right, because on mesh analysis, you can, because you're doing it with meshes, and you don't care about node voltages per se, you don't need to pick a ground.
That's right, because that's exactly right, because all of these things are just going to be Ohm's law and these currents. That's great. Interesting observation. So you can see an example here with mesh analysis. There is no concept of ground needed for the solutions. Now, let's talk about the difference between nodal analysis and mesh analysis. The main thing to remember, even before we get into this, is that nodal analysis and mesh analysis will give you the same answer. Each of those methods will give you the same answer for a given circuit of the type we're dealing with in this class. In other words, if we give you one of these linear circuits that we've been solving and you apply nodal to it, you're going to get some node voltages, and you can use Ohm's law to solve for any currents that may be of interest. And if you use mesh analysis on the same circuit, you're going to solve for mesh currents, and you can use Ohm law to figure out what the node voltages are. And in both cases, the answers are going to match because there's only one solution to any of these circuits. Okay, but the question still arises: which one should you use given some arbitrary circuit?
And to answer that, let's consider what nodal analysis does versus mesh analysis. Remember, nodal analysis uses KCLs to determine node voltages. So node voltages are unknowns. And mesh analysis uses KVLs to define mesh currents. So really the main difference is in nodal analysis you're doing KCLs. In mesh analysis you're doing KVLs. So to a large degree, in many cases, the choice is based on the complexities of solving KCLs versus the complexities of solving KVLs. Now what sets that? Well, there's certain things we can use to kind of guide our decision-making process. For example, we look at the circuit and we see it as supernodes or supermeshes, which may complicate or simplify analysis. That's one thing that could guide you. Another is you could look for trivial equations. For example, if you saw a current source driving directly into a node, then you might want to do a KCL because that's easy, it's trivial with a current source. So that would then guide you to use nodal analysis.
So like what you're saying is if I see a supernode in a circuit, I might use mesh analysis to not have to deal with the supernode, or if I see a current source, you know, in between two meshes, I could do nodal analysis to just avoid that altogether, right?
That's right. That's right. So these are guiding principles that you can use.
You know, but I'll say, to be quite honest, I always use nodal. I mean, I found that of all the friends I have that are engineers that do this kind of thing, you end up favoring one method or the other, usually. I mean, we all know how to do both, but I find that I do make a lot less mistakes when I consistently do nodal analysis, even if I'm dealing with supernodes.
That's a reasonable statement. In fact, as you've seen throughout, we tend to stress consistency. We ask you to solve loop equations with a clockwise loop, and we say just do it every time because that prevents you from making silly mistakes. The same is true in terms of choice of analysis techniques. You'll find that many people will pick a technique that they get very comfortable with, and then they just work with that technique. Michel has just told you he tends to use nodal analysis. I also tend to use nodal analysis. Having said that, however, of course, that doesn't mean that in a test, if you're told to solve a problem using mesh analysis, you can get to use nodal analysis.
Yeah, don't blame us if you're given you know, a mesh problem and you write the answer to this is I would like to use nodal and I solved it with nodal. So you're all learning, and so you're going to have to learn to do both of them. But
that's right.